All right, so in this module, we're going to start looking at phase diagrams and specifically the solubility limit. All right, so here's a basic phase diagram that you may have all seen before for water. And it gives information on phases at particular temperatures, pressures, and compositions when we get to that. However, this is only a one component or unary phase diagram because we only have one component, water, H2O. And so this one shows temperature on the x-axis and pressure on the y-axis. And we have the different regions of the phase diagram correspond to different phases. So in the bottom, you see vapor or steam. In the top, you see liquid or water. And then we have over here on the left, solid or ice. And so those are the three regions where you see different phases. However, there are also different areas. So we have areas here, here, and here, but between the two areas, there's a line, right? So this line right here between liquid and steam is where vapor and liquid are in equilibrium. So right on that line, you can have both phases. And the same thing with this line over here. Solid and liquid would be present at the line. And on this line, solid and vapor would be present on this line. So the lines, the lines tell you, in this case, equilibrium between two phases. And there's a one special point, right, where those three lines intersect, where all three phases, vapor, liquid, and solid, are at equilibrium. And so we call this the triple point. So you may have heard that term before. And so all three of those phases can be present at the same time. And so in this case, it's about 0 Celsius and a pressure of 0.01 atmospheres. And so again, this phase diagram gives us information about what phases are present at different temperatures and pressures, right? So you can kind of think about, room temperature is roughly 20 degrees, and then atmospheric pressure is about 1 atmosphere, right? And so here is where we are typically at on Earth, and you see that we have liquid water. If it gets colder, you see that you can get solid ice. And obviously, if it gets hotter, you can start to get steam, or if you lower the pressure as well. So that's what this phase diagram will tell us. And I want to make one sort of caveat for all of this, is that in all of these, we talk about phases at equilibrium. And so this concept of equilibrium means that there can be situations where at 20 degrees, ice is present, right? So, it's, again, room temperature. You may have ice in your cup. So that doesn't mean that solid ice can't exist. It just means that it's not at equilibrium, right? So if you wait long enough, that ice becomes liquid, and that's what happens. So when we talk about equilibrium, we're typically talking about allowing things to kind of come to their steady state or resting position. So that's what we're looking at with this type of diagram. So now let's look specifically at a solubility limit. And all a solubility limit is a maximum concentration that a single phase exists. So let's look at an example here. And this one might be an example people are familiar with. This is basically sugar water. So water and sugar, those are our two components. So in this case, we do have a binary system because it has two components. So binary just means two. And those two components are sugar and water. And so here we're looking at composition on the x-axis and temperature on the y-axis. And what we see is that here on the left, we have a liquid and a liquid solution. So basically that's sugar water, right? And then above a certain point, which is this blue line, we have a liquid, the solution of water and sugar, but we also have solid sugar. And if you think about this, right, if you try to add more and more of a material, of a component that can dissolve, right, like salt or sugar into water, right, there reaches a point where the solution can no longer handle that, and so it won't dissolve, it'll stay as solid. And that's what's happening here. And so the solubility limit is just the maximum concentration for which we can have a single phase. So the syrup or sugar solution is a single phase, but once we have the solid sugar, that's two phases, right? So that's the solubility limit. And one thing that we see here is that temperature changes it as well. So this solubility limit isn't constant, it actually changes, it has a slope to it. And so let's investigate that a little bit more. So solubility tends to increase with increasing temperatures. So that makes sense because a lot of times when you want to make a sugar syrup or salt solution, you boil it, right? And that's because we see here that at this low temperature of 0, we can get about 60 weight percent sugar. However, if we increase the temperature up to 100, that goes up to 80, roughly 80%, right? So solubility, that's the general trend of solubility, is that it tends to increase with increasing temperature. So this is true for sugar solutions, but also true for alloys and other materials as well. So that increased temperature allows for more solubility. And so we can kind of look at a given position and we can see that if we have 60 weight percent, or sorry, if we have 70 weight percent sugar at about room temperature, so 20, then it won't dissolve, so we'll have solid sugar. But if we heat that up to near 100 degrees, it will dissolve, right? And so that's a classic way to increase the solubility. But the other converse part of that is that if we cool it back down, this is kind of showing that if we further increase, we'll still get two phases. But what I was saying before is that if we have that 70 weight percent sugar solution, if we cool it back down, you would expect eventually the solid sugar to precipitate back out. All right, so here I have a quiz question involved with the same solution, the same phase diagram that we've been looking at. So what I want you to do is determine what the solubility limit for sugar in water is at 20 degrees. So do that real quick, answer that in the quiz, and then come back and we will discuss. All right. So we're looking for the solubility limit of sugar in water at 20 degrees. So again, the red curve in this case is the solubility limit. And so we basically need to find 20 degrees and then match where the solubility limit is. And so that is right around here. So if we kind of draw that in, 20 degrees, follow it over to the line, and we see that that is roughly 65. So not exactly, but around 65% sugar. So again, what this tells us is that anything under 65 weight percent sugar would be a syrup at 20 degrees, and then anything above that would be a syrup plus sugar. And I do want to make the one caveat here because you might have had this happen. Again, keep in mind, this is an equilibrium diagram, so you wait long enough for these equilibrium phases to occur. If you dump a bunch of sugar in water, right, it's not going to instantaneously become a syrup. There are other factors, we call them kinetics, which is basically has to allow for the movement of molecules. And so there is an issue with that. But if we wait long enough, that sugar will dissolve. But just keep in mind that even if the equilibrium diagram here says that you can put 65 weight percent sugar in water at room temperature, don't expect that to occur instantaneously. There is a time factor that's involved there, and that's the same thing involved with if you have a cold glass of coffee or tea or whatever it may be, and you try to add sugar to it, it is very difficult to dissolve, even though it will dissolve eventually, right? You just have to keep stirring and stirring. And so that's the equilibrium part. It takes time because there's a kinetic factor where we need the movement of those molecules to get into equilibrium state. So that's another consideration that you have to think of outside of the equilibrium phase diagram.